Hi, welcome everyone to the machine learning using Python linear regression session 6, which is nothing but module 4 and part 1. This is about linear regression. So, Jaymeet Vasava, our instructor, has been doing an excellent job. He has been running us through. This is the second of the series. First one he did for the Python programming. Now this one is for machine learning with Python, and this is uh, a good one to get into the details of machine learning. With, of course, this is mathematical part of it. Then logistic will follow, but this linear regression is the one of the fundamentals one which should hear from Jaymeet. Go ahead, Jaymeet, take over and make the presentation. Thank you.
Thank you, and hi everyone. Welcome to this machine learning using Python session 6, which is on linear regression. Before this, we covered descriptor analytics and a short intro to the machine learning and what is machine learning. So the goals for this session would be to understand the simple linear regression, then spread the data, to discuss the steps for building a machine learning simple linear regression model, and then learning to build a model. So some of those steps are to use a data set, to spread the data set, and to train and test the data set on for the model. So this session will be discussing about the simple linear regression. So simple linear regression is a statistical technique used for finding the existence of the association relationship. Basically, what you are doing is you have two factors, and you are what we can say as an independent and dependent variable. You have an independent variable which will cause an effect, and we have a dependent variable on which we will see how much effect we got. So for example, we have soil erosion and rainfall. Rainfall becomes our independent variable. As the rainfall will vary, we have our dependent variable, which is soil erosion, which will vary according to the independent variable. In this case, rainfall. The same example goes for work experience and salary, and vehicle's age and its resale value. The vehicle's age can be anything, and depending on that, the vehicle can have a resale value on it being affected. So these are the examples for simple as well as multiple linear regression models, but we are only discussing about a simple linear regression, which means that we have one independent variable and one dependent variable. So a hospital trying to understand the cost depending on the patient's weight, and then an insurance company trying to understand the healthcare cost and aging, then an organization trying to understand a product's revenue generated by that organization and the related factors associated with, like the price of itself and the price of the competitor's product, then the promotion expenses or the marketing expenses that it takes in order to market the product. And then the fourth one, the restaurant willing to know the relationship between the customer's waiting time after placing the order and revenue that they generate. So in a way, you can say that restaurants trying to know the relationship between how much revenue is affected for the wait time of the order. Then an e-commerce website like Amazon or Flipkart try, trying to understand the relationship between the revenue and the number of customers who visit the portal, who clicks on the products, who or how many items are on sale on the platform, or the average discount percentage. Then banks or other financial institutions willing to understand the impact of variables such as employment rate, marital status, balance in the bank account, rainfall, etc., on the percentage of non-performing assets called NPA. So whenever we try to build a model, will have a framework which we can follow, and we can depending on the use case, we can change those steps if needed, but we can follow this framework of steps which help us to build a model. So the first step is to collect the data from various sources and store it for our use. When this happens, we call it an ETL, which is extract, transform, and load. Extract the data from various sources, transform the data for our use, and load the data into our place where we can directly use it for our own use. The image below kind of depicts what we want to use for our model, but the image generalizes the use of extracting the data to using to be used by the organization or for the project. So even if the extraction of data, or even if you have the ERP system, which is the enterprise resource planning system, it can be time consuming, and it is often said that working with whenever we try to work in machine learning field, we are 80% spending our time on the data and 20% on the models and stuff. So this is the table that we'll be using in order to keep track on which kind of steps that we have that we have discussed. So the first is collection of or extraction of data from different sources. And then the second step is to pre-process the data. Now, as the image says that we will start from image cleaning, then integration, then transformation and reduction. Image cleaning is remove or a correction of inaccuracies in the data, like missing values or outliers, or mistyped values. Then comes data integration, which combines the data from multiple sources to create a unified data set for analysis. And then transformation is to convert data into a suitable format or structure, such as normalization or encoding categorical variables. And then comes dimensionality reduction, reducing the number of features while retaining the essential information, often using techniques like principal component analysis. So I hope the data processing part, which is depicted in the image, is clear to you. But we'll also go through some of the points that additionally are stated in the slide. So before the model is built, it is essential to ensure that the quality of the data for issues such as reliability, completeness, usefulness, accuracy, missing data, and outliers. So data imputation technique may be used to deal with missing data, which we discussed for data cleaning, use of descriptive statistics and visualization to identify the existence of outliers and the variability in the data set. Then comes many new variables can be derived from the existing variables and can be used in the model building, which is a part of the Deriving new features is the part of the feature engineering part. Then comes the categorical data must be pre-processed using dummy variables as a part of feature engineering and before it is used in the regression model. So this is something that anyone who is new to the regression models need to understand that it does not take categorical values. So those categorical values have to be converted into dummy variables in order to work with. Uh, so let's say there is a field called color. So color has three values: red, blue, and green. So in order to say that color would be replaced with red, blue, and green, and in order to show red as the value, we'll give the red as value 1 and the other two colors as 0, and the same goes for all of them. So in order to get the categorical values, and that is the way we can use it for a regression model. So the two steps that we have discussed till now are collect or extract the data and data pre-processing. The third one is dividing the data set into training and validation sets. Now so whenever we are trying to know to work with our data, we have a data set. So that data set is typically uh, split it into three parts. The first, I would like to have your attention towards the lower left image. The data set is first split into training set and testing set, and then that training set is further divided into training set, uh, or we can say that that training set is further uh, got a portion of validation set, or is further divided into a validation set, and the proportion is also the same as it is shown in the image. The training set consists of almost 60 to 80% of the data. The If we are taking 80% of data training set, then we are taking 10% for validation as well as the testing set. So the first is test, and also you can see the variability on the proportion of the different sets on the image on the bottom right, the training set, validation set, and the test data or the test set. So first is the training set. This is the data on which the model is going to train on and learn about the data. It will contain almost all kind of variety of data, so that the model gets the capability to generalize the data that it is working on for the better quality and the diversity. As the better quality and diversity of the data is, the better is the performance of the model. Next is validation data. Validation set. Validation set is usually used for tuning the hyperparameters which are used to train the data. So after training, there is a validation step. In validation set, use the we configure the model on how to learn the data and whether the model is learning the data in the way we expect it to, for the training data that it's learning on. In a loose manner or in a layman term, you can say that whether the model we are checking in the validation set, whether we are doing a good job at, or whether the model is doing a good job for learning the data that we have given to it. So the validation set comprises of 10 to 15% of the total data set, but this may vary based on the number of hyperparameters. More hyperparameters may need a larger validation set. If the model's accuracy on the validation set exceeds to that of the training set, it is considered to have generalized well. So the reason to use a validation data as As said, it's used for hyperparameters, which which takes the parameters, certain parameters, and those parameters are can influence on the way the model learns. So let's say there is something called as a learning rate. So if you keep a higher number for the learning rate, then it will affect the way the model learns. A slower learning rate can take a much more time, but also learns the data well. So those are the kinds of hyperparameters you deal with while training the model. Then comes the second reason is to prevent overfitting. So overfitting is generally a situation where is a sorry overfitting is a situation where the model is able to learn the training data well, but is not able to generalize other kind of data. So anything other than the training data, it is not able to work with, and also includes the noise in the data or the outliers in the data, and then hence the overall poor performance on the new data. So by using a validation set, you can monitor performance and ensure that the model does not just memorize the training data, but can generalize well. The last is a training testing set. Now, independent testing set is basically used for testing the model performance. Now, in this phase, the model is not going. The model has not seen this kind of data before. So something similar might have seen, but not the same kind of data. So the testing set kind of gives it the scenario of dealing with the real world data, and the testing set provides us how the model might perform in real world. So it's so independent of the training set, but has somewhat similar type of probability distribution of classes, and is used as the benchmark to evaluate the model, used only after the training of the model is complete. Testing set is usually a properly organized data set having all kinds of data for scenarios that the model would probably be facing when used in the real world. Often the validation and testing set combined is used as a training testing set, which is not considered a good practice. If the accuracy of the model on training data is greater than that of the testing set, then the model is said to have overfitting. So this data comprises of 20 to 25% of the total data available. And for the split of the data sizes, you can see these kind of images in order to have a rough idea about it. There is no hard rules about it, but it depends what kind of data or what kind of splits portions do you want to use. So till now we have discussed three steps for building a regression. The last was data splits. Uh, starting from the starting from one, we have the extraction of data from various sources. Then comes the data pre-processing, where we improve the data's quality, basically like handling missing values, making sure that outliers are not missed, or typographical errors, or whether they are actual outliers, and then dimensionality reduction techniques like reducing the number of features or creating new features also. Then comes the data set splits, splitting the data set into train, validation, and test set. The fourth is using the descriptive analytics or data explorations. So basically using the data set to visualize the data into different form. You can use a scatter plot or bar plot, as you can see on the bottom left or you can use a box plot to in order to recognize the outliers. You can see that in the batsman section there are three dots, and there is a wicket keeper section, there is a dot as well. So those are the outliers within the data sets that it is showing. So for such information, we can use descriptive analytics and use different plots in order to get uh, more uh, visualized insight into the data set that we are using. So we have discussed the fourth step for descriptive analytics to visualize the data in order to uh, see the whether there are outliers or not, or different insights. You can also guess the distribution of the data from scatter plot and stuff. Now, building the data. The model is built using the training data set to estimate the regression parameters. The method of ordinary least squares is used to estimate the regression parameters. Just a second. So OLS is used in order to estimate the values of parameters in the regression model that we will be building for. So OLS is a technique used in linear regression models to find the best fitting line for a set of data points by minimizing the residuals. What is residuals? You can say residuals as errors too. So the difference between the observed and the predicted values. So if we, let's say we are trying to predict the salary of an MBA graduate based on what marks they got in their 10th standard. So when we plot the graph, you can see that there are different numbers that are uh, that are being plotted, denoted by the actual salaries, and then there is a line called regression line. Now, when we use a linear regression model, that line is supposed to be as nearest possible to all the points that are showing up. So we have built the data using the data set as well as the data set, and build the and seen what the regression lines tells us about the data we are working on. So we'll be using the OLS, or ordinary least squares, to build the model. And do not worry, we'll be discussing these steps exactly when we'll be building the model. So these are just a representation of what we'll be doing in order to get a rough idea before we actually build it. So building the model, then the sixth step is model diagnostics. Now, model diagnostics is to know or to be following the rules, or whether we have followed certain rules that we were supposed to follow while building the model, as well as building the data set. So regression is often misused, since many of the time modelers fails to perform necessary diagnostics tests before applying the model. Before it can be applied, it is necessary that the model created is validated for all the model assumptions, including the definition of function form. If the model assumes or model assumptions are violate it, then the modeler must use remedial measures. Now, if we are using regression, there are certain assumptions under which the model is going to work. So those assumptions, if not cared or just for any mistake, they are not considered, then the model will have different kind of insights, and those insights can give us uh, confidence of false reading, for confidence on different kind of conclusions than we were supposed to make. So the sixth step after building the model is was the performing diagnostics. So performing the checks that we were supposed to have. Seventh is validate the model and measure the model accuracy. Now, as we have already discussed about the overfitting, a major concern in analytics is overfitting. The model may perform well on a training dataset, but may perform badly in validation dataset. It is important that to ensure that the model performance is consistent on the validation dataset as well as the training dataset. So the model may be cross-validated using multiple training and test datasets. So validate the model and measure the accuracy of the model. Then decide on model development.
Deployment.
Sorry. So decision regarding the model deployment. The final step in the regression model is to develop a deployment strategy in the form of actionable items and business rules that can be used by the organization. Now, this now there can be certain business rules that should be performed while developing a model, like a certain kind of risk cannot go further than a certain threshold value or so, or and such kind of logics, business logics are applied before the model has been deployed for the real world data in order to get the insights to be used. So these are the 8 steps that you can use in order to have a reference for while building a regression model. So collect the data, for process the pre-process the data, then split the data for the training, test, and training, validation, and test. Then comes in visualize the data, build the model, perform the diagnostics or check the model, then validate the model and measure the model's accuracy, and decide on model development.
Deployment.
Oh yeah, sorry. Model deployment. So as we are building the simple linear regression model, this session will be a lot more theoretical heavy, as we will be discussing the mathematical representation of what we are doing. So linear regression model, the linear regression can be presented as this, where y is denoting y equals to beta 0 plus beta 1 x plus epsilon. Now y means our dependent variable. Beta 0 is our intercept. Intercept is basically what if the value of the independent variable is 0 and y's value is not 0. So that is what the intercept does, then or represents. Then beta 1 is the coefficient of the independent variable, how much change in beta 1 will cause the how much change of independent value by 1 will cause the value to increase of y. So that is what the coefficient does. So beta 1 is the coefficient and plus epsilon is the error or the estimate of error, or how much variation there is in our estimate of the regression coefficient. So for the data sets in n observations of xi, yi for I equals to n, where n is the for the n observations or the size of the data set, we can represent the formula as yi equals to beta 0 plus beta 1 xi plus epsilon I for the ith observation. So as we discussed about in the model diagnostics, that there are certain assumptions when we work with linear regression model. So the there are 4 assumptions that we'll go through. The first is the linear relationship. There exists a linear relationship between the independent variable x and the dependent variable y. Then comes the independence, that they are the residuals or the errors are independent. There is no correlation between the consecutive residuals in time series data. Then comes the homoscedasticity, which means that we have constant variance in our data set. The variance is basically how much the data is dispersed. So we have a constant value, constant variance around the data set. Then comes the normality. The residuals of the model are normally distributed, or the error of the model are normally distributed. So the properties for simple linear regression, uh, the mean value of y for the given xi value is given by the beta 0 hat plus beta 1 hat x. Now, this hat says that it's an estimated value. So y follows a normal distribution with mean beta 0 hat plus beta 1 hat x and the variance epsilon. So as we'll be discussing this simple linear regression with the help of a data set which contains the MBA grads salary and what they scored. So what we are basically trying to do is what amount of what percentage or what was their score in 10th standard, and depending on that score we are trying to guess what will be the salary of an MBA grad student. So as you can see that there is a data set which contains 3 columns: the serial number, the percentage they got, and the salary that they have. So now we'll be building the regression model for us. Now you can see that we will also state the steps in order to build this regression model, and how much it can be. We can follow the framework that we used for framework of steps that we used for before this. So as we have already have the data and the data is already pre-processed, we can kind of have a combined or uh, not use the step 1 and 2 for the discussed steps, but we will be using the pandas and numpy libraries and use it to create the read the data set as well as create the data frame. Then we will be splitting the data, so that is something that's common. Then we will also use visualization technique wherever we need it, and also build the model which coincides with the fifth step above and the fifth step in the framework as well. Then we'll be performing the diagnostic and validate the model also. So which coincides with the performing, sorry, the sixth step and the seventh step in the table. So we import the necessary libraries for NumPy and Pandas, and then print the first few records in the data set that we have. So we read, you can see how the data frame looks like for the record now, for the records being printed. So you can also check the first record 62% and 27 2,70,000. Next is the info regarding the data set. There are three columns: serial number, percentage, and salary, which takes the integer, float, and integer values respectively. And there are total 50 entries, 0 to 49. And the memory usage is 1.3 KB. Next is identifying our X and Y variable, which are the independent and the dependent variable in our data frame. So if we compare it with the mathematical form of linear regression that we discussed, then we can say that X is our percentage in grade 10 and Y is our salary. So we'll be using the OLS API of stats model. So we'll be using the stats models library and using the API module, which has the OLS or ordinary least squares method, which takes the two arguments, the dependent variable and the independent variable. So sorry, if I go for the order, then independent variable X and dependent variable Y. We will also include the beta 0 value, which is the intercepts value as 1 in the column. So we'll do that by first importing the stats model.api as SM, and then give the X or the independent variable as a constant. So which will create an additional column of constant with value 1. So you can see the change that it shows. The X has a column before it called constant and has the value 1 in it. Now we'll be splitting the data set into training and validation sets. So we'll be using the scikit-learn or scikit-learn's model selection module, and with that we'll be using that train test split, which takes a number of arguments, though we are not going to use each and every one of them right now. But you can see in the syntax that the first argument it takes is in terms of arrays. Then comes the size of the data set, the train size, the random state. The random state is basically whenever you are splitting the data set, if you give it a number, let's say 42, then it is always going to create the same kind of split containing same kind of data at number 42. So it's kind of a recognition number. So if just in case if you want to create or recreate a result, you can use the random state for the particular data set, and you can use it in order to recreate it. Then comes shuffle. it takes boolean values, true or false. It, as the name suggests, that whether we want to shuffle the data set or not, and then stratify. Uh, by default, it has a none value, but the data is split in a stratified fashion using this as the class labels. So now we'll be splitting the data set. So according to the actual framework, the bigger framework that we used, which had 8 steps, according to that, we are on the third step. So we'll be splitting the data set. First will be the train X and train Y, the X features of the training set and the Y containing the values of response variable for the training set. Then comes the test X and test Y for X features of the test set and the values of the response variable for the test set. So as discussed, we'll be using the scikit-learn some model selection dot train test split. So we'll be using the train test split for the values train X, train Y, test Y, and the train test split takes the following arguments as also discussed over here. The first is the independent variable, second is the dependent variable. Then comes the size of the training set. We will be taking 80% of the data denoted by 0.8. Then comes the random state. We'll be giving it the value of 100. So as the training set contains 80% of the data, the rest 20% will be used for validating the model. Next is fitting the model. So we are using stats model as a SM. So sm.ols. OLS is the ordinary least squares that we will be using for in order to estimate the values of the parameters in the regression model. So when we give it the name of MBA salary LM, those the values that will be returned by the OLS will be saved into that MBA salary LM, which will save the model's parameter, the accuracy measure, as well as the residual values among other details. So printing the estimated parameters and interpreting them. So for getting the parameters and getting our values, so when we print this MBA salary LM and give and print its parameter, so this is the kind of output that we get. You can see that there is a constant value, then comes the percentage in tenth and the data type. So the constant is the beta 0 value when we compare it with the mathematical expression. Then the 3560 is the value of the coefficient of the independent variable. So for every one single change of in X, we will get the value of X to be increased by that amount. So 3560, every increase in X will have this change. You can also compare the value, this mathematical representation with y equals to mx plus c, but we have where the constant or the intercept is c and the mx value as the coefficient as well as the independent value. So as we are discussing about the predicting the 10 marks of MBA grad students based on what they got in grade 10th. So this is the way that we'll be doing. Import the necessary libraries and then use MBA, use the data set to be read using the pandas library and giving it the name of data frame as MBA salary DF. When we print the first few records of the data set, this is what we get. Then the information regarding the data set. Then using the x value for our independent variable as well as adding the constant. That add constant method helps us to add the constant value. As you can see that percentage in grade has an additional, and this has an additional column of a constant with the values of 1 in it. Then comes the dependent variable of salary. We are trying to predict the salary based on the marks that we and that these MBA students got in their 10th grade. Then splitting the dataset using the scikit-learn's model selection module and the train test split method. So we have the test and train being selected from X, the Y and test Y being selected from the Y that we created over here. The size of the set is 0.80% of it, and the random state that we are giving is 42. So that there is a change that is intentionally kept, which is keeping the random state as 42 over here and in 100 in the slides. So you can check you can follow both the random state in order to get different results. Now, fitting the model, we will be using the OLS method and giving it the value of train Y and train X. Train Y for the dependent variable as well as train X for the independent variable, and used to fitting the model. Then using the fit method to get the values. So when we run this and use the .fit method, we get all the values that the OLS method gives us in being saved into this MBA salary LM. Now that MBA salary LM will be we can print the parameters using .params, and we get this as an output. So this is remember that this a different random state was used compared to slides, so that's the reason the numbers are different. So this was the framework that we followed and that we discussed about in the very beginning, and then we built our model using the steps, as some of the steps won't be needed, as we already have a data set to be used. So now we are on the performing diagnostic, which is the step 6 according to this. So uh, model diagnostics are used for validating the model before using it in our real world scenarios. So there are different measures that are used to validate the simple linear regression models. So we'll be going through five of them. The coefficient of determination called R squared, then hypothesis testing, the analysis of variance or ANOVA for the overall model's validity, then residual analysis to validate the regression model assumptions. I remember that we discussed assumptions regarding the constant variance, linearity, normality of residuals and stuff. Then the outlier analysis, whether there are outliers present in it or not, and which can affect the regression parameters. So coefficient of determination, or called as R squared. So this is the linear regression mathematical representation, which can be substituted with these values. So the first is so yi is substituted as something called as SST. SST is nothing but the sum of squares of total variation. So yi minus yi will become yi minus y bar, which is the mean of y, whole square, for the sum. Sorry, I read it wrong. So summation of I equals to 1 to n yi minus y bar whole square. Now beta 0 plus beta 1 xi will be substituted with a summation of I equals to 1 to n yi hat for the estimated value of ith observation of y, minus y bar whole square, which is nothing but the sum of squares of regression, explained variation due to the regression model, and then for that term is added with the summation of I equals to 1 to n, where yi minus yi hat whole square for the sum of squares of errors. So our mathematical representation becomes a yi hat equals to beta 0 hat plus beta 1 hat xi. Now that is for the estimated values of y. So as the SST, SSR, and SSE, the R squared will have the formula of SSR divided by SST, which is for equals to 1 minus SSE by SST. So the coefficient of determination, or the R squared test, has the following properties. The value of the R squared lies between 0 and 1. Mathematically, R square is a square of correlation coefficient, where R is the Pearson correlation coefficient. Now higher R squared indicates better fit. However, one should be careful about the spurious relationship. The next step is the hypothesis test for the regression coefficient. So we have beta 1 equals to 0, and we can conclude that there is no statistically significant linear relationship between two variables when beta 1 or the beta 1 is equals to 0. Which is our null hypothesis. The alternate hypothesis is beta 1 is not equals to 0. So we'll be conducting a t-test statistic, a t-test, which will be a two-tailed test, whether the value is smaller than or greater than mean. So t-test alpha by 2 is equals to beta 1 hat divided by SE beta 1 hat. SE of beta 1 hat. SE is nothing but the standard error of estimate for the regression model coefficient. So SE beta 1 hat is equals to SE divided by square root of xi minus x bar whole square, where SE is the standard error of the estimated value of yi and the residuals, which is given by SE equals to square root of yi minus yi hat divided by n minus 2. So as also mentioned, that t-test will be the two-tailed test with t distribution with so which follows a t distribution with n minus 2 degrees of freedom. It's a and you can see why n minus 2, as we are taking beta 0 and beta 1, which is loss due to the estimation of it. And just for a t distribution is something similar to the normal distribution, but with thicker tails. Then comes the analysis of variance. Or ANOVA in regression analysis. We have the null and the alternate hypothesis for it. The null hypothesis states that beta 1 till beta k have all the equal values, which is equals to 0. Whereas for our alternate hypothesis, not all regression coefficients are 0, which basically means that it can the coefficients value till k, some of them can have similar values, but not all of them. So we'll be running the F statistic or the analysis of variance test on the for this, which F stat which is denoted by F. So F equals to MSR by MSE, where MSR is nothing but a mean squared regression and MSE is a mean squared error. Further, MSR and MSE will be substituted by SSR by K and SSE by N minus K minus 1. So F-test is used for checking whether the overall regression model is statistically significant or not. Then comes the model diagnostics. We'll be running the summary over the MBA salary LM that we have discussed, and you can see that that summary, whatever we have discussed or ran through over here on these concepts in a theoretical way, those numbers will be found. So you can see that in this summary, there is a snapshot of the screen which contains the result. So you can see that there is a R squared value which says 0.211. Then comes the statistic value, or F statistic value of 10.16. Then comes the coefficient standard error t value and stuff. So based on the table, as you can see that R squared value is 0.211, which means that a model accounts for the 21.1% of the variation in salary. Then the p-value of the t-test is 0.0029, indicating a statistically significant relationship at a significance level of 0.05 between the percentage of grade 10 and the salary. So the probability value of the F statistic model is a 0.0029, demonstrating that it signifies that it's a significant relationship between the p-value as well as between the percentage that the student got in 10th and the salary they are getting. So it's important to note that in simple linear regression, the p-values of the t-test and the f-test are the same because they test the same null hypothesis. Additionally, in the case of a simple linear regression, the f statistic equals the square of the t statistic. So f equals to t square. And then comes a residual analysis. Residuals are nothing but errors. So yi minus yi hat, or the actual value minus the predicted value or the estimated value. So residuals are also known as the salvage value assessment, which is a statistical method used to evaluate a linear regression model's performance by analyzing residuals. It helps identify and rectify model issues, assess assumptions, and detect outliers for improved efficiency. For that, we perform the following checks. The residuals are normally distributed. Variance of residual is constant, or or what we call as homoscedasticity. Then comes the functional form of the regression is correctly specified. And there are no outliers. So first is the normal distribution of residual, which we'll check with the help of the probability plot, also called as PP plot, which compares the cumulative distribution function of two probability distributions against each other. So in the code, we'll be using the plot method of stats model to draw the probability plot. So you can get this plot using this code. We'll be importing the necessary libraries such as matplotlib and seaborn. Then we'll use the residuals of the MBA salary and plot the graph using the prop plot. Also, we'll use the user line at a 45-degree angle, and you can see that in the image, whenever we are the data points lies just around the line that we have seen, which means that it is normally distributed. So the diagonal line is the cumulative distribution of the normal distribution, and the dots represents the cumulative distribution of the residuals. So since the dots are close to the diagonal line, we can conclude that the residuals follow an approximate normal distribution. Next is the test of homoscedasticity, or the test for the constant variance. That the the values, whenever they are plotted, they are scattered all over the graph rather than forming a certain particular kind of shape. So an important assumption in the regression is that the residuals have constant variance called homoscedasticity across different values of the predicted value. If variance is a non-constant, then it is called heteroscedasticity, and its graph contains a funnel shape of residuals. So in order to test for the homoscedasticity, we'll be using the standardized residual values, and we'll get these values by making a custom function called getStandardizedValues, which will return us the values by getting the values and also deducting the values from that of a mean and the standard deviation of the values used. So, there are a couple of reasons to use the standardized values. This method transforms the original values into standardized scale with a mean of 0 and a standard deviation of 1, facilitating better comparison, interpretation of coefficients, numerical stability, and adherence to regression assumptions. So when we get get the standardized values and plot it on the graph, this is how the graph looks. So let's just discuss the code here. So first we get the standardized values from the custom function that we have made for a get standardized values. Then we'll be using the scatter plot in order to get those values to be plotted using the get standardized values as function and the values from the MBA salary LM, and the fitted values gives us the value of them. Then the gets the rest, then plot just a second. Yeah, so then using the get standardized values of the MBA residuals or the errors in the MBA salaries that is captured by the model, and then in the end plotting the model, giving it the title, X label, and the Y label. So this is how the graph is created, and this is how the graph looks. So you can see that the data points are not forming any kind of funnel shape. So a similar kind of screenshot is displayed on the slide. On the left, we have the homoscedasticity or a graph with constant variance, and on the right we have the heteroscedasticity or with a non-constant variance. So you can see that when it's a non-constant variance, it forms a funnel shape in the plots, from which we are able to see that it's a non-constant variance. Next is the model diagnostics for outlier analysis. Outliers are the extreme ends of the data set. Some of them might be a true value for the natural variation in the population, but some may result in different entry of the data due to different reasons. It can be for mistype errors or equipment malfunctions or measurement errors and stuff. So when dealing with outliers, you have to recognize whether they are actual outliers or are caused by some reason. So the reason why we need to retain the true outliers is because these are just representation of the natural variations in the sample of the data set that we have or we are working with. So as the outlier is a crucial step, as it contains some of the red items within the data set. These outlier significantly deviates from the majority of the data points and can sometimes indicate problems, errors, or conditions that warrant further investigation. So what do they show? They show large deviations from the mean values, as well as outlier presence can significantly influence the regression coefficients. So in order to test those influential observations, we have 4 tests: Z-score, Maha, Lanobase distance, Cook's distance, and leverage values. Going with the starting with the Z-score. It indicates how many standard deviations a data point is from the mean. It is calculated by subtracting the mean from the data point and dividing by the standard deviation. So it is only used for univariate outliers, but do not account for multivariate relationships. Then comes the Cook's distance, which is a distance measured for the influence of data point on the overall regression model. It combines information about the residual and leverage of a point, which quantifies how much regression coefficients would change if a particular data point was removed from the analysis. The points with a large Cook's distance are considered influential. So if Cook's distance is higher than 1 or 2 times the square of the k by n, where k is the number of coefficients and n is the sample size, the observation is likely to be influential. The common threshold is d is greater than 1 for identifying highly influential points. Then comes the leverage values and Mahalanobis distance, which measures the influence of observation of overall fit of the regression function, the leverage values, and is related to Mahalanobis distance. So the leverage values of more than 3 into k plus 1 by n is treated as highly influential, whereas k is the number of features in the model and n is the sample size. Now Mahalanobis distance is a multivariate distance measures that rescales variable based on the eigenvectors to remove correlations between variables. Now, Mahalanobis distance can also be deferred in terms of Euclidean distance. Is that like Euclidean distance? It measures irrespective, just scale down all the values into 2D plane. The Mahalanobis distance, it's going to be same, and it can be. You can imagine that what would be the values of different data points from the mean of it. And that is what Mahalanobis distance is doing. So Z-score identifies univariate outliers. Mahalanobis distance identifies multivariate outliers. Then Cook's distance measures overall influence of the regression model, and leverage value assesses the influence on predicted values. These measures can be together used to identify the influential observations that may unduly affect the result of the statistical analysis that we are doing. So using the Z-score, as we run the Z-score for our for for our MBA salary DF, and we are trying to predict the salary. So we'll give the Z-score as MBA salary. So as you can see that according to that, we are getting no results. So there are no values according to the Z-score for our case. Then comes the Cook's distance. We are using the get influence method from the MBA salary LM, and then using that into the MBA influence, and then using MBA influence for the calculating the Cook's distance. So you can see that a graph is made for the data points that we have, which shows which calculates the and the Cook's distance for the salary. So you can see that none of the values are going further than 1. So and there are no outliers according to the Cook's distance. Then comes the leverage values, which also uses for the Mahler-Nobel distance. So the size of the circle is proportional to the product of the residual and the leverage values. So larger the circle, the larger is the residual and hence influence of the observation. So that is how the values are leveraged, and that is how it affects the parameters and the different parameters of the model while learning. So this leverage values is used using the stats model, graphics, and regression plots. So using the influence plot as well. So we'll be using the influence plot for the model values that we have saved on. So we have saved it on MBA salary LM. So this is the plot that we get for it. Now making the prediction and the accuracy on the model that we have made. So predicting using the validation set, the model variable has a method predict, which takes the x parameters and returns the predicted values. So we'll be saving these values into pred_y and use the MBA salary ln to use to make the predictions on test x. So pred_y contains the values that we get from the model, and the mean square error, root mean square error, and mean absolute percentage error are some of the frequently used measures in order to assess the accuracy. So testing the accuracy of the model of the predicted value that the model is going to give us for the predictions that are made on the test X set. So we'll be using the scikit-learn matrix in order to use the R2 square and the mean square error for calculating the R squared score and the MSC values. So MSC will be used through NumPy, as NumPy has the square root system. So we can use the root mean square error for the RMSE. So the remember that R2 R squared we discussed before also, where you can see that that is the formula to the reference that we have discussed. R squared equals to SSR by SST equals to 1 minus SSE by SST, which is displayed on the top right. So we will be implementing this same formula for our total sum of squares. Now when our R score is 0.68, so it says that 68% of the variability in the dependent output attribute can be explained by the model, while the remaining 32% is accounted for. So the R score, R2, R square score is desirable as it signifies a better fit for the model to the data. Now the range of the R2 score or R square score can range from 0 to 1. 1 indicating model perfectly predicting the dependent variable, while 0 meaning that model does not explain any variability in the dependent variable. Then comes the R2 score, the usage of it. The R square is commonly used in regression analysis to assess how well the model fits the data. It helps in comparing different models and understanding the proportion of variance explained by the model. Now, R2 and mean square error, both of them take predicts the y values and the actual values and calculate the accuracy measures. So as I also mentioned that root mean squared can be simply calculated using numpy, as it has the square root uh, square root method. So R2 having 0.156 indicates that the model accounts for 15.6% of the variation, and the root mean square error value having 73548.043 represents the average error model makes while predicting the outcome. So smaller the RMSE value, better the model, and RMSE value of 0 will indicate that the perfect that the model is perfect. So in statistical inference, calculating the prediction intervals. So specifically predictive inference prediction interval is an estimate of the interval in which the future observations will fall with a certain probability given that already has been observed. So for calculating this prediction intervals, we'll use the significance level of zero point 0.1 or zero point 0.1, giving the prediction at confidence interval of 90%. So for calculating this interval, we'll be using the WS prediction STD method, which returns the prediction interval while making a prediction. So this WS prediction STD method, it takes the first argument as a model, the second argument as the independent variable, and the significance level as mentioned over here, alpha. So when we have made the prediction regarding the predicted intervals, you can see that this is the kind of output that we get. You can see the number, the percentage that the student got, the prediction that is made in pred y, and pred left and right are nothing but the lower and upper bounds of the prediction intervals. And in the end, when we try to plot the graph, this is how the graph looks like with the regression line fed to it. After the model has been fed, we can use the regression line, and this is how it looks. So let's discuss the code. So we start with the model diagnostics. Remember that we use the summary 2 in order to get the summary for the model that we have used, and the R score value, R squared value, and the F statistic value. Then comes the residual. We check for the residual analysis for the normal distribution of the residual. We import the necessary libraries, and then test for the homoscedasticity. As you remember that these are all scattered and not forming any funnel shape, so which shows that there is a constant variance, and we are using a scatter plot in order to make this plot from the model that we have made, and using the dot fitted values and getting the standardized values of the residues from this. Then comes the outlier analysis using the Z score. So we import the scipy.stats and import z-score from that. Calculate the z-score on the salary, and if it's greater than 0 or smaller than -3, and you can see that we are getting no values for it. So according to z-score, there are no values. Then calculating the Cook's distance, and as you remember, none of the values got past 1. So there are no values according to Cook's distance. Then using the stats model graphics dot regression plot, sorry, stats model dot graphics dot regressions plot, and using the influence plot in order to build this plot. The influence plot takes the model as the input, and when we get the values, you can see that the size of the circle is proportional to the influence it has. Then making the predictions after checking on it, making the predictions on the sets. So we have our model, and we make the predictions on the test set. So, and saving it into predictions of y. So we have so as we are making the predictions on these, we will be checking for the testing testing the accuracy of the model, or the testing the accuracy of the predicted values. So we will be using R2 square and mean square error for it. As said, we can use the R2 square and the R square score and the mean square error for checking the value. We got the R square score of 15.6% or 0.156, and the value for RM is value of root mean square is this. Later we so in the last we make the predictions using this test X, and use the WSLS prediction STD for on our model with this argument values, or the parameter values. First being the model itself, second being the test set on the alpha value. Next is creating the data frame on predictions of y, which contains grade that the students got in n%10, or in grade that the students got in grade 10, then which will be taken from percentage in grade 10 from the test split of x. The same goes for prediction of y from the grade y, prediction of left, which shows the lower bound of the confidence interval, and the upper right for the upper bound of the confidence interval. PLT.figure is nothing but the size of the figure. Then we use plot in order to plot the regression line for the grade or let's say for the the values for grade that we got, as well as the grade that the students got, that we equated from here, from this set, and the predictions that are made and saved in the prid.ydf. Then comes the field between. The field between is nothing but this color change you can see. Those color change is done by fill between, and you can just simply see that how which arguments it takes. It takes prediction ydf grade 10 percentage, from grade 10 percentage the prediction y, prediction y right. So the lower and upper bound of the predictions of y from the prid.ydf. We can give it a color of light gray, the alpha value, as well as the prediction interval as the label. Then creating the scatter plot within which this will be appearing. So first is the MBA salary DF, and which will contain the percentage in grade 10. Then comes the salary, the color, the label that it shows. Then these are nothing but the simple labels of X, Y, title that is appearing over here, the Y and the X label. And in the end, the plt.show, in order to show the plot. To make sure that it shows the plot, it's not necessary, but still we can show it. So this is the plot that we get when we make it. And in the end, the predictions that are made are saved into prid.ydf. So these are all the predictions that are made with the lower and the upper bound of the predictions in prediction interval. So if the guy has got, if a person has got 83%, this is the value that is predicted, and the value can lie between this minimum of this value or maximum of this value, and so on for all the records. So this is it for this session, which was on simple linear regression. We discussed a lot on simple linear regression. We discussed a framework. We discussed a framework of points which you can use to build a simple linear regression model, as well as you can use. We also separately made or followed some points where we were building our own regression models. Then we discussed the various steps as well as the measures it takes in order to diagnose the or check the assumptions that are followed by a simple linear regression, as well as testing the values of the R square or with the R square or root mean square error. So thank you. This was the session regarding the simple linear regression.
Thank you very much, Jaymeet, for the excellent presentation. And what we'll do is we'll put it on the record so that people can appreciate the details. Maybe they will not see the entire thing. Half of it, even if they see, they will be able to understand and grasp and do their exercises. And thank you very much. And with that, I will stop the recording.
Oh.